Hello, everyone, and welcome to the Foundational Statistics for Forensic Toxicology webinar series. Throughout this series, we will hear from Sue Paring, Quality Manager with the San Francisco Office of the Chief Medical Examiner, and Aria McCall, Technical Lead with the Tarrant County Medical Examiner's Office. Today is Session 1, Intro and Basics. So now, without further delay, I will turn things over to our presenters.
Good morning or good afternoon or good evening, depending on what part of the world you are in. I wanted to welcome everyone to the first of 6 sessions, and thank you all for joining us live or via recording later. My name is Aria, and I'm a toxicologist over in Tarrant County, which is in Fort Worth, Texas, or in the Dallas-Fort Worth area if you're not familiar with the region. So basically, that's where the Dallas Cowboys play. I just want to make it clear to everyone that I am not a statistician. I am just a toxicologist. All of the statistics I have learned, I've learned on the job, so to speak. So you can be assured that the sessions all have more experienced people, my subject matter experts, to help answer questions and to participate or host in some of our upcoming sessions. All right, so a little bit about how these classes came to be. So statistics is becoming a more utilized tool for process control, for our testimonies, and representing the quality of our work product. So many times you may wonder if you're doing these calculations correctly, or if you understand enough about what you are doing. And because I'm not a statistics person and I've never had a college level statistics class, gasp, I've had to survive primarily through using the internet, Google, some inherited Excel sheets, and the guideline documents for my learning. I also have to give honorable mention to the fine toxicology community for putting up with all of my questions that concern stats, because I definitely had a lot. So I was always a little concerned about what I'll call my lack of knowledge in this particular area until I really started to realize that I'm not alone. Many of us have not taken statistical courses. You know, we are scientists. We didn't really anticipate needing to have a double major in statistics as well. So if you are like me, then you are not alone, okay? I have always had questions that I always wanted to have answers, and I didn't really have a good venue for it. These questions are things like, what exactly does statistically significant mean? Or what does statistically insignificant mean? Like, what is the basis for that particular statement? Other very common questions are things like, what is a trend? We are all supposed to be monitoring for trends. We're all aware of that through our accreditation guidelines. But what is it really? Is there a mathematical way to calculate trend? What am I really looking for? And then we have questions about bias. You know, when does it really become bad? Do I rely on just the ASB document to do that? And what can I do about bias? How should I explain that well? And where do a lot of these 20% acceptance criterias that we have for many of our validation type documents, possibly in your own laboratory for your SOPs, you have plus or minus 20%, but where does that come from? Who decided that it was going to be 20%? So in addition to my questions, while I was traveling down this path, I started to develop an idea of holding a series of courses or one very long course, you're welcome, because it is broken up into 6, about dealing with some real basics and some real fundamentals of statistics. So the goal of this particular series is going to be to normalize our limitations of statistical knowledge. It's perfectly fine not to know things. You want to have an idea about what you may not understand very well and what you can explain very well. So today's class for sure is going to try to provide a foundation, just a very basic foundation that my other presenters are going to build upon with their mathematical calculations and more complex ideas and things that we use in toxicology. And because statistics is such a broadly based discipline, we're really trying to focus our series directly to our toxicology folks. So while the concepts are definitely very broad and can be applied to a lot of different forensic concepts, here we're trying to just bring this to the toxicology community. We wanted to keep it manageable, not super scary, not overwhelming as statistics can become very quickly. And we wanted to let people know there's always more things to learn. Like certainly this class is not going to be the end all be all. So just to get an idea of who's here with us today, I have a polling question for everyone. I think everyone knows how to utilize this particular activity. There we go. So how do you feel about your knowledge of statistics that you use in your job now? Are you glad it's not your responsibility? You're curious, but it seems like a lot. You know, you do it, but you're not 100% sure on if you do everything the best way. And then number 4, you crush it. You're like, give me all the calculations. I want all the spreadsheets, essentially. And I'll let you guys know what my answer is here in just a few minutes. We'll just give people a chance to give us some answers. So as the answers are populating, when they look like they close down, we'll probably give a little bit of a summary of what some of our results are. But I will tell you, when I started my career, I was definitely the first choice, which is glad it is not my responsibility. And I am definitely with the vast majority of you. I am definitely a 3 now. I do it, but I'm not 100% sure if I do everything the best way. So to be clear, nobody's alone in their knowledge. We have 6% of the people here that are ready to crush it, which I applaud you, and I will need you to drop your contact in the chat list because I will be contacting you later. All right, so let's get on with it here. So I will say some of our upcoming classes that are coming up, we've already seen a slide about these. So we're talking about intro, distributions and standard deviations, statistical tests, which will be very interesting. And then kind of a little back and forth between myself and Sue Paring about the use of controls and some other control chart elements, calculation of type A data from control data for measurement uncertainty. And then the one I'm kind of excited about, which are our fireside chat. So this is going to be a chance to ask questions to my roundtable of subject matter experts. So I will be there to help kind of moderate a little bit, but this will be everyone's opportunity to ask questions. And in that regard, I want to encourage people to be proactive. So we're going to be gathering all of your questions in the chats. So be specific as you can and go anonymous if you feel embarrassed, but please don't. You've already heard my questions. You should not be embarrassed. You've already seen the poll. Feel comfortable with what you don't know and go ahead and ask. The fireside chat is going to go over as many of the gathered questions that we either don't get to in a particular session or haven't been covered in a session that is going to be occurring later on. And we'll kind of go through those in kind of a, back and forth sort of style, but it'll be your opportunity to ask the questions that you want to ask about the statistics you use in your laboratory and the questions that you have. So really, I would love to see the chat filled up with questions so that we'll have plenty of things to go over, things that you want to know, not just the things that I want to know. Because remember, my questions are things like, what's a trend? What does statistically significant mean? I want to be able to get those answers out of these 6 sessions. So it's for both for you and for me. So please feel free to participate in those. So today's goals are going to be very foundational. We're going to cover where statistics is needed or where it is encountered in our day-to-day experiences in the lab, where you may see it frequently, what statistics are used for and why it's important, and some data analysis, statistic terms and definitions. So I just want to make it clear that these sessions are not meant to replace a college level course or a formal online course that is concentrated in statistics. I wish it was, but it is not. We're just going to look on a more focused toxicology angle for some of the basic statistics and some of the ways we use them in the laboratory. Remember, statistics are applicable in a wide variety of disciplines and industries, and have different applications or goals in each one of them. So here, these sessions are basically for our practicing professional toxicologist. But if you are from a different discipline, I do want to welcome you. Certainly in some of these basics that we're learning, there is an application probably that you can use. These are foundational and they do apply across many different disciplines, but we're going to focus our examples mainly for toxicology. So I want to talk a little bit about career growth. I know the next few slides won't apply to everyone here. This is just my own perspective. And it may not be how your career path has looked or how it looks now. This is a general type path, and it reflects mostly my own career as I have grown working in toxicology. So some of you may have come into your career having specifically gone in to do method validation only. But I think for a lot of us, we come in just as little baby scientists, and we kind of grow and learn and embrace forensic toxicology. So in light of that, I have two other polling questions, but here's number 2. I would like everyone to drop in the chat how many years you have been in the field. And we'd like you to just use a whole number for your years of service. And so I'll let everyone get started on that, and then I'll tell you what we have planned for this information. All right, so the question 2 is up. How many years have you been in the field? So again, just enter a whole number. That's all we want to have put in there. And so what we're going to do with this information, and we're going to gather up all the results of this poll, just the number portion, not any individual identities, so don't worry. And if I understand correctly, my co-host Sue Perring may run some stats on it to use as a fun example in another session. So please participate in the poll and just type a whole number for the years of service in the field. And what I'm going to do is I'm going to give more people an opportunity essentially to participate in the poll. So I'm going to leave it open while I go ahead and move on. And I'll probably give a quick reminder for anyone who may have missed this slide before I close the poll, so people can still get in on it. But for right now, let's go through a little bit about where stats are encountered and needed. And this is a little about that career growth that I was talking about. So in the first few years, when you come into toxicology, your exposure essentially to statistics, and again, this doesn't apply to everyone, but when you're new, you're basically using the statistical framework that's already in place. You are learning how to color within the lines. You're learning the parameters that are used for passing in your particular lab, which means QC limits, what your curve criteria are. You're doing a lot of reading, you're learning the job flow, but at the end of the day, you're working in the framework of statistics where you're trying to figure out, can I report this? Is this good data? Can this number go on the report? So you're working within a framework that's already been established for you. Then we kind of move on. Now we're going into basically our intermediate years in the middle, and lo and behold, you get more job responsibilities. At this point, you may be asked to evaluate reagents, maybe evaluate some purchased QCs. Now you're in charge possibly of a particular assay, and you're going to be in charge of those looking for trends. Participating in generating validation data, you're starting to become more and more aware of guidelines and accreditation standards, because at 6 or so years, you have certainly had the pleasure of going through one of our on-site accreditation assessments. So you understand the busyness that goes on in that particular time frame. And you probably have a knowledge of the basics of the measurement uncertainty for the purposes of explaining for testimony. So your exposure to statistics is getting a little more rigorous. You're starting to learn these things, you're really participating in it, you're stepping into it. So when you are a little more advanced or mature in your career, you have more job responsibilities at this point. You may be in charge of actually generating the measurement uncertainty, evaluating and monitoring all control charts, and evaluating the various calibrations that may be in your lab, like for pipettes and balances, those types of certificates. You may be in charge of calculating all of the validation data at that point, or new target values for controls. You may have to designate what the replication criteria is for casework. And now you are in charge of the application of these accreditation standards or guidance documents for that matter. So at any of these stages, you could probably find yourself, what's the meaning behind the number we get? Or what does this tell us or not tell us? Because as toxicologists, generally we're concerned when data or a calculation is acceptable. Our reasoning may be due to various guidelines or criteria that we've either been established for us, such as the ASBs, or in your own standard operating procedures. And you just want to know what is the meaning behind it. Now you've got a little more experience and a little more room to breathe. And I think poll 2 has, we may still have a little bit of time left for poll 2, which is just to type in a whole number for your years of service. I saw it disappear from my screen, so it's possibly that it's done, but I just want to give everyone another couple of seconds to type in their years of service if they can. And then we'll move on here in just a moment. And again, we're just collecting this particular data so that maybe we can use it for some fun statistics later. I say fun statistics. All right, so we will move on here and go ahead and close poll number 2. So what are statistics used for? Why is it important? So our primary application is data analysis, and we're going to go through some of the examples for data analysis, but this is how we would see it in the laboratory. You know, our control charts, our curves, calculations that we do, explaining measurement uncertainty, and a lot of our technical documents that we may receive for validation and journals and everything. So, data analysis. So, it's important to analyze data. That seems very straightforward. So I like the parallel that this particular slide has with our, journey that we've had, that I explained about your career growth. One is the framework of learning to monitor your controls, essentially. You ensure consistency and reliability. That is the business we are in. Quality controls and acceptance criteria. Then we also use it to summarize and describe data. So with descriptive statistics, which is more math, essentially. So averages, mean, median, standard deviation. Then 3, we're using it as a whole, essentially, to draw conclusions about our sample of data. Do I have an expectation that this assay is going to continue to produce good results? And this is why I know that. So that's even more math, essentially. So to summarize, it's basically a situation where you have facts. You're dealing in the framework of facts that have already been established. Then you kind of get more of a whole picture of how an assay is at a particular moment in time. And then you get more of the future state. It will do it in the future because I have all this information from the past that allows me to make those inferences about the future. All right. So now we're going to get into some definition and terms and how they are related. So here I have a typical list of common terms for statistics and ones that we see very frequently in the toxicology laboratory. Certainly, if you have ever done a validation, you have participated or have at least been exposed to a lot of these, including the measurement uncertainty also. All of these terms are things everyone should be familiar with in their laboratory. But we're going to dive into these a little bit deeper so that we can build that basic foundation that we were talking about earlier. So population. Population is an entire group of items, essentially. It's usually a little unwieldy to actually work with, but mathematically, it is usually represented as a capital N. So population, capital N. Because the population is usually a little unwieldy to work with, we have sample. So a sample is a subset of the population, and it can be used to draw conclusions about the entire population. It's generally more efficient and less unwieldy to use a sampling rather than a population. And mathematically, we see this represented as a lowercase n, which makes sense, right? We are a subset of the population, which was a capital N. So now we're just a little baby brother, a little lowercase n. So degrees of freedom. And I'm going to be very honest about this. I almost eliminated this slide when I went to create it. Degrees of freedom is far more complex than I originally thought. But let's just go through the basic definition here. So the degrees of freedom is the number of independent or free to vary values that go into calculating a statistic. And while it's related to the sample size, the degrees of freedom will always be less. So it's represented generally as a lowercase df, although I have seen it as an uppercase df in various documents. And it is n minus p, where n is the sample size and p is the parameters tested. I'm sure that makes perfect sense to everybody. So in light of the potential complexity of this term, I'm going to keep this very simple for us. This is what, as a toxicologist, you will primarily use. Depending on the calculation that you are using, the degrees of freedom can change. Fine. But generally, on a day-to-day basis, whoa, hold on, not every day, but in your laboratory, generally, you are going to be using the sample size -1, or df equals n minus 1. Now, if you happen to be using a paired t-test, for example, the degrees of freedom is going to be n minus 2. So it's just important to keep in mind if there's a particular calculation that you are using and it's new to you, you can look up the degrees of freedom essentially, and you will be able to find it here. Now, other sessions may delve a little bit deeper into the degrees of freedom and what you will use, but generally in the laboratory, I have only ever really used df as n minus 1. All right, central tendency terminology. So these are all words we're very familiar with. So average, mean, median, mode. So average usually is mean to me, but it can actually refer to any of these central tendency measures, which I actually didn't know because the English language loves to be confusing. So mean is adding up all the values in a data set and dividing it by the total number of values. Mean or average is typically what we hear for this particular calculation. And then you have the median, which is when the data is arranged from ascending or descending order, it is the middle value. So a lot of times, as an example, this one's used primarily for, possibly drug results, so that, one overdose, one methamphetamine packed stomach smuggler doesn't skew the results or the meaning essentially of the data. Then you have mode, which is the number that appears with the most frequency in a data set. And I don't see this one very often at all. Generally, if you would see this in readings, possibly in journal studies. Traffic safety data, I think, is probably one of the areas where I've seen mode used. All right, so let's look at a typical example of something that we see in toxicology, essentially. So this is an insert from an FTC, and we'll probably see this again. And I just want to draw attention to the fact that here we have our capital N, which now we know is used as a population. And they use the terminology mean here, or average, as we more commonly see it represented. And then we also have median, which is, again, the middle value when all of the results are arranged in ascending and descending order. So here's just a quick example of where you can see some of these statistical terms in toxicology. All right, so now we get to some results of testing terminology. And this explanation and the targeting example is something that pretty much all of us are familiar with. The targeting system represents what accuracy and precision means. This is a great visual example that I've used many, many times. So accuracy is how close results are to a true or known value. And precision is how close results are to each other. So here in the upper left-hand corner, we have what can be described as accurate and precise. All of our data is grouped in our yellow or our bullseye targeting zone. Then in the lower left, we have what would be described as inaccurate but precise. Our data is still grouped tightly together, but now we're further away from our actual target or reference value. In the upper right-hand corner, we have what can be described as accurate but imprecise. I could have probably gotten those X's a little closer to the target, but just bear with me. Accurate and imprecise. Our data is spread, but our average is very close to the target. And then in our lower right, we have what can be described as inaccurate and imprecise, meaning our data is not grouped together and it's nowhere close to our reference value. So in our terminology, we already have two newer terms. We also have inaccuracy and imprecision. So the opposite of accuracy, inaccuracy, the opposite of precision, essentially imprecision. So this is the start of a graphic that I'm going to build upon as we go forward, basically to get a better visualization of how our data fits or looks for the terms that we're going to go over. So our reference value line here in yellow is like the middle part of our target illustration. And as we move forward, I'll be filling in with mock data or testing results to help us visualize the terms that we're going to be discussing. Now, there's nothing wrong with the targeting system. I just feel like this particular reference is going to help us to visualize some of the terms that we're going to go over. So here, ideally, just to give you an example, we would want all of the data to be clustered around the true or reference value, which would be described as both accurate and precise. I mean, we all wish our data is both accurate and precise. That is what we strive for. So here's another common document that you would see in your laboratories where we see some of these terms. So here's a very typical calibration certificate of a pipette you might receive in your particular laboratory. And already we see the terminology of the accuracy as a percentage and the precision as a percentage as well. And you can see the actual and target values listed there below. So I used a slide earlier where I gave out the definition for accuracy and precision. So I'm going to change it up just a little bit as we go forward, and I'm going to change it to relating to accuracy and relating to precision. So I'm going to, let's just add the definitions back in here just so we have a reminder of what both of these things are. Accuracy relates to how close we are to the true or known value, and precision is about how close the results to one another. And I'm going to start adding in terms into our graphic as if they relate to accuracy or if they relate back to precision. And now we're going to look at our graphic with these two definitions built in now. So our yellow line is still our target or reference value, and the inaccuracy becomes the distance from that reference value to where our test result actually fell. The spread of the data around a particular central point becomes our imprecision. Now, our first example was a calibration certificate for a pipette. So here's an excerpt from a booklet that comes basically with all of our pipettes. So here we see two more terms, systematic and random error. So these are all typical booklets that are put in when you purchase a new pipette in the box. This one happens to be for an Eppendorf pipette, and it uses the terminology of systematic and random error of a particular pipette at a level or type that you are using as your reference data here. So let's see where systematic and random error fit in when we're talking about accuracy and precision. So systematic error relates to the distance between the tested results and the reference value. So it falls under the umbrella of accuracy, while random error refers to the spread of the data. So it relates back to precision. Just as an aside, while I'm here in the United States presenting, I think it's important for people to remember that depending on what part of the world you may hail from, the terminology that's favored in your publications or documents may be different than what we typically see out of the US. So as we just saw in the Eppendorf pipette booklet, it favored the terminology of systematic and random error over accuracy and precision. And Eppendorf is based out of Hamburg, Germany. So just a little quick note, now that you know where systematic error and random error belong, you can easily make that association in your mind as to what the measurement relates back to. So another terminology that we commonly hear is bias. Where does bias fit into our graphic? This is a term that we've always heard. It sounds bad, but what does it mean? So bias is the tendency of a measurement process to over or underestimate the value of a population parameter, and it's measured by the percent difference from the target value. So based off of the terminology in the graphic we've already covered, I think it's very easy to see where bias is going to fall into our graphic. The terminology of percent difference from the target value basically gives it all away. So bias fits under accuracy, as we probably all already knew, and it fits in with our inaccuracy and systematic error, essentially. So I have kind of an interesting side note. Well, I thought it was interesting, and it kind of surprised me a little bit. So this is one of the documents that I reviewed while preparing for this particular talk. And I did a search of this document for the term of accuracy. I wanted to see how they defined it. Now, this is a 46-page document. I did search all 46 pages, and I was kind of surprised that there were no matches found. It was, I don't know, it was just surprising to me. What it does have is 58 instances of bias being used. So the section of accuracy and precision is actually bias and precision in this particular document. So I wanted to cover this because this was always very frustrating to me. Are we the same? Is accuracy and bias, are they the same? So I wanted to go through this just real quickly. So remember the definition, how close for accuracy is how close are the results to a true or known value. And that is a fine definition for our purposes. So embrace that definition. If you want to get a little more specific, depending on what definition you are looking at, I looked at NIST and a statistical book. The accuracy is a property of a single measurement, or the agreement between a test result and an accepted reference value. So you can think of it as that, a single measurement, if you would like. And then when you do that, bias becomes more representative of a sampling of data, essentially not just a measurement. Remember, bias is giving you information about the entirety of a process. So it needs more than one actual measurement. And because English is fun, accuracy can be used in a more general way just to describe a process. Just remember my slide that says relating to accuracy as well. So when we look back at this example, we have percent accuracy and percent precision, but we know that it's taken at least a few measurements here. So this is probably also could be described as bias as well. And then we have percent precision. Here, we understand that systematic error is now relating to our accuracy system and that these results are relating back to our precision. So we're getting into a couple more terms to round this out. We have variation, or the spread of the data, and it's measured by, most commonly, the standard deviation, or how far from the mean. And then we have coefficient of variation, which is simply the standard deviation divided by the average. And it's also represented many times as a percentage, so a percent CV. Now we're going to put them into our graphic. Now, it's very easy at this point. If variation is the spread of the data and it's measured by standard deviation, we pretty much know where they're going to belong in our graphic as well. So each one of those phrases relates back to precision, along with random error and imprecision. They're relating back to this bell curve of the spread of our data. Now, hopefully this particular graphic has been helpful to you in terms of being able to categorize whether a terminology is related to accuracy or if it's related to precision. Again, there's nothing wrong with our targeting system when we're explaining, but I like the way this one kind of breaks it up very simply in the graphic so that we can see exactly what we're talking about when we're talking about a spread of data from our test results. So I hope you did find it helpful. So a couple more terms here. We have reproducibility, which is the replicate results that can be produced on a similar instrument by anyone. And both of these terms can be seen in validation. And as an example, so for reproducibility, you may be comparing old method results with a possibly tweaked up newer method, essentially. So you're comparing those two data sets, essentially. For repeatability, you have replicate results by the same person done under conditions in a short period of time. For repeatability, an example would be essentially serial injections from one vial on your LC-MS, something like that. Now, both of these experiments are descriptors of precision. The data generated by both of these types of experiments are going to get you precision type data. So here we have our example from our CAP insert booklet, and it contains some of the terms that we have already looked over. So we have our target concentration, or the target spiked amount, we should say, which ideally would be our yellow line in our graphical representation, right? And then down here, we've pretty much covered all of these guys. We have population, we have mean and median relating to our central tendency terminology. Then we have a standard deviation here, I clicked too quickly. We have our standard deviation and our coefficient of variation. And we also have the minimum and maximum, which represent the lowest result that was received and the highest result that was received in this particular data. So we'll go into this just a little bit more. So this is a result that your particular laboratory may receive as a summary of your testing results. So we have the mean here. So we have your result that you turned in from your laboratory. Then we have the mean instead of average, but that is what's represented here. Then you have your standard deviation. Then you have labs. Then you have SDI, which is the standard deviation index, or Z-score, which, spoiler alert, I believe Sue Paring, the presenter for next week, is going to have a little bit something about that in her talk. And then you have your limits of acceptability. So if you're within the limits of acceptability, you get the satisfactory. If you're outside of it, you get unsatisfactory, which means you have a lot more paperwork to be done in your laboratory. So on this particular slide, I do want you to take note of the mean, the standard deviation, and the labs here, because I'm going to show you where your evaluation statistics, as they're labeled, come from. So we've seen this a couple of times now. Here we have our FTC insert. And down here under the all methods, you can see that the lab number is represented by our population here, 109. Then the mean here, 12.2, is represented in our previous page as well. Then you have the standard deviation here, and now you have the percent CV. So, which you'll remember, the percent CV is calculated by dividing the standard deviation, which is 1.29, which is represented here, by the mean, which is 12.2. Then you multiply it by 100 for the percentage, and that will give you the percent CV of 10.6. Okay, our last polling question. So my last polling question here is, I'm curious if you have had a formal statistics course. Did you have one in college? Did you take it as a continuing education course? I mean, technically, you know, just on the job to get by isn't a formal statistics course, but you can put in 3, and then never. And so my particular result would be never. That would be my guess. And if you are one of those people that took it in college, my part 2 question would be, did you like statistics when you were in college? Or did you pass statistics when you were in college? All right, let's see what we got. Oh, wow. A lot of you took it in college. I am so sorry about that. Okay, now I want the people that took it in college to give me your impression of if you liked it or not in college. Because I never took it, but we'll see. All right, everyone. What's next? So our next class is going to cover distributions and standard deviations. The graphic that we have here is one that I pulled together for a different talk. It's an actual representation of real data to give an example of normal distribution. And I wanted to go ahead and put up a slide about our basic information that I used in this particular talk. Now, what we're planning on doing is doing a collection of all the informational resources from all of the sessions. We will be actively compiling those after each presentation so that we can present that during session 6. And we will make that available to the people who participate in the sessions. That way, nobody has to really worry about copying anything or having any basic slides. So just know that that will be available to you at a later time for sure. So at this time, I just wanted to say thank you to everyone for joining me today. I am looking forward to the next talks, essentially, as they come up, the one next week as well. So at this time, I think we're going to see how the question and answers are going to go.
Yeah, thank you, Aria, for providing us with the foundational statistics for this webinar. I'm Catherine Bollinger, and I'll be moderating some of the Q&A questions that have come up. And then we've also had Sue Paring is going to be joining us, and David Heller from RTI. He's in a statistician background, so he can kind of support Sue and Aria as we go through. So I want to start out with a question about, please explain the percent accuracy and the percent precision that was written on the slide related to pipette calibration. And so I'm going to turn this one over to Aria for that slide.
Okay. Do you want me to pull up the slide for that? Would that be helpful?
That'd be helpful. I'll buy you some time as you're doing that. I'm still laughing about that came through the chat that they called it sadistics instead of statistics.
Oh,
I
that's
think we got to
fantastic.
rename this webinar series, action to sadistics. I love it. Yeah, as Aria is pulling that up, also in the Q&A pod, if there is a topic, you saw the title of each of the sessions in the chat earlier. If there are areas of interest, of course, we'd want to highlight the content that Aria just presented, but if there are others, feel free to drop them in the Q&A pod. That way we can include them, and if not, we'll make sure we hit on it as best as we can in the fireside chat. Thanks. Go ahead, Aria.
All right, so percent accuracy and precision, essentially. So my subject matter experts are here in case I misstep. But again, these are descriptions. So this percent accuracy or accuracy as a percentage is could actually be represented as the bias, essentially. And the precision here is representing the spread of the data. We have a group of data that's been used to generate these two particular numbers, the actual result meaning 0.55, which would be our bias in this particular area. The target is 1. It has to be less than that by the manufacturer's definition. And the spread of our data is 0.19, where the target is 0.5 or less in order for it to pass calibration, essentially. Is there anything more you want to add to that, Sue?
Oh, that's great.
Okay.
Dave, anything you want to add?
No, I think that covers it, as long as it answers the question. Yeah.
All right, so I'll go down to the next question. This one is about understanding what the percent CV is. And if you can explain that a little bit more when you're talking about percent CV.
And I'll leave that for someone else.
Okay. Sue, do you want to take that one and talk about percent CV?
Yeah, I'm just reviewing this. Okay, the standard deviation divided by the average CV also represented as percent CV. Similar to the previous question, actually, percent accuracy, percent precision can be represented in a lot of ways. It can be in absolute terms, so in the units that you're talking about, or it can be presented as a percentage relative to the actual thing you're measuring. So to put that in a little more context, you might consider a CV is a standard deviation relative to the average of the thing that you're measuring. If we're talking about the years of experience we have in this field, right, that might be on the range of 0 to 35 or even 40 years for our most seasoned toxicologists who are still dedicated to the field, right? And in relative to that range, the standard deviation might be something as a percentage of maybe 10% or 20%, right? If you gave that as just the standard deviation might be something like 4, right? But relative to 4 years, that's 10%. It gives you a feel for the scale of what you're working with. Let's contrast that example with something like how many nanograms per milliliter of diphenhydramine are found in drivers, right? That might be a much narrower range, and that scale might be from 0 to, I'm just making a number up, 100 nanograms per milliliter, right? And it might be something that's much narrower. And depending on the units, that standard deviation may be different. But regardless of the units, when you represent it as a percentage, you get a better feel for, okay, what is that relative to the number we're actually measuring? Dave, anything you want to add to that or say it a different way? I know sometimes we get really narrow in our forensic toxicology terms.
Um, no, I think that was great. I think just to um, let's see, emphasize the point is that basically it allows to like compare across different items. In other sort of like survey stats is actually called like the relative standard error, so that you can see like how much variation there is for a certain item you're measuring versus another item you're measuring, and they don't have to be related at all. So it's basically the way to sort of talk across measures rather than specific things of measurement, I guess, in your world. Yeah.
Nice.
Yeah, that's great, Dave. Good point. And I
Thank
think
you.
that can also be used to describe in my diphenhydramine and drivers example. If you have diphenhydramine in drivers and then you're looking at diphenhydramine in the postmortem population, right? Those ranges may be different, but the relative standard deviation or the percent CV may describe kind of that distribution, a little nod to next session, in a way where you can actually talk about the two sets of data together.
Okay, and thank you,
Nice.
Sue. So we're going to stay a little bit on the percent CV. We had a question here about what is an acceptable percent CV.
Ooh.
So
Hmm.
Aria or Sue, do you want to take that one?
I don't know what an acceptable one is.
Yeah, I'd say the easiest answer is for what? And to answer your question with a question, what is it acceptable for? What are you using it for? What are the risks for it? Much of the national standards that are coming out are very specific about, the acceptance criteria depending on its application, right? And I'm saying in the chat, depends on the type of testing you're doing. It depends on what you're using that metric for, right? If you're talking about, you can imagine that there could be a wide range of things for what you might be using CV for. Is it appropriate to describe your quality control for measurement uncertainty? Is it appropriate for your performance during method validation? Or is it appropriate for, a general description of your business metrics of, how many days your average turnaround time is? Your tolerance and your risk acceptance for that type of statistic may be very different depending on that. Now, with that said, instead of just to leave you with another question, is to say, well, there are references available to give you some guidance. The national standards, the ASB standards do seek to address some of that, but there's no real replacement for just good old-fashioned critical thinking. What are you using it for? What are the risks? What happens if it's too high? And to really think through the scenario that is presented with the specific application you're talking about, to consider, well, you get to decide, well, how much do you really want? How much are you really willing to accept? Aria, Dave, anything you want to add?
No. Again, this is why I have subject matter experts to tackle your questions and my own. So fill up the chat. We'll get to them eventually for sure.
Dave?
The only thing I'll add is that sort of in related to like survey statistics, we'll look at the percent CV or the RSE for like if it's above 50% is usually a standard for like as far as precision, where we wouldn't want to output that estimate to represent the population. Like there's too much variation there that we're going to say that this is the number, because a lot of times people look at the estimate, but they won't look at the standard error. So you don't want to so you sort of want to curve that using applying suppression to different sort of estimates. So the sort of CV or RSE sort of comes into play there, where they'll set a standard 50, 75 and something like that. So, but I think the way you explained it was perfect.
Yeah, that's interesting, Dave, because it kind of suggests that sometimes we can use that data to then determine how we represent the data. In other words, you're using precision to control whether or not you use an average as an estimate or not, to say, is this a responsible way to describe it, or is this actually not very representative? And that's certainly true outside of surveying world too. Even we're not really talking about surveying driving populations. We're just doing our work and testing and collecting this data. But when we do go to represent it, is the data that we're representing representative? Understanding that sometimes the audience does not look at the standard deviation, and keep that in mind. Right.
So we've got time for maybe one or two more questions, and then we will definitely get to those at the fireside chat or later on. So one of the questions we're going to go back to standard deviation is how many samples are needed to calculate a meaningful standard deviation?
Ooh, that's a question I have. And Sue,
Okay,
if
I'll
you
start with my answer.
okay.
Well, actually, maybe Aria, you start with yours. How would you answer that?
No, I was pointing at myself because I have those questions. That person asked my question. I thought it was fantastic.
Did you plant it? Okay, this is my attempt at an answer. I would say if you're trying to describe that sample, I would err on the side of like 30. That was taught to me a long time ago. 20, kind of 30 is good. The more, the better. But I know there's way more complex studies that can go behind it to talk about statistical power, and that's why we have Dave here.
Yeah, I'm to that question is for in 2 minutes, it's going to be 30 was also what I was always taught in school. Through work, we work on things that are a bit larger, so 30 never even comes into play. But yeah, I think how do you answer a question badly? I think I will say it depends, but 30 was always the chosen number that was always taught, because eventually reaches a normal distribution. Another plug for your future courses. So we just leave it at that for now. But
well, and I want to remind people that your questions now will help us with future questions or examples because of the ones that we're gathering from the chat. We want you to ask questions so that my future presenters and our future sessions can maybe get an idea of where we as toxicologists are missing some basic knowledge. So it really only helps that you ask the questions. We may not get to all of them, but I love the questions that I've seen in the chat. Like I said, I have similar questions like that also. So when you ask the question, it's only going to help mold some of our future sessions as we go forward. So I absolutely appreciate the attention to the questions. And I know it's frustrating not to have like this really solid answer, but maybe we can build it into a future session that we haven't quite fleshed out to help answer some of these questions where it's it depends situation. So I just wanted to make that note to everybody.
Great, thank you, Aria. So we're approaching the top of the hour, and so we're not going to have much time to finish up the questions here, but we will at another time. So I want to thank you all for joining us, and I hope we will see you back for our session 2, which is May 23rd, about distributions and standard deviation at 2 p.m. Eastern. So thanks everyone for joining us today.
Thanks everybody.
As you depart, we kindly ask that you take a minute or two to complete our post-event questionnaire. The link will be pasted in the chat and also appear as you exit the Zoom room. Your feedback helps us improve our outreach efforts and continue to provide the best experience possible. Thank you again for attending, and we hope everyone has a great day.